Okay, we're going to talk about this phase lag that happens between the phase of the displacement and the force, that driving force. So we have the sinusoidal driving force. This is the phase of the driving force, and in the steady state, when time has passed beyond the damping time constant 2 over gamma, the displacement forgets how it got started. All the initial conditions are gone, they are all washed away, and it just oscillates at the frequency of the driving force, but it's not going with the driving force. It usually has it lags, or if delta is negative, it can go ahead. That's kind of a little crazy, but depending on the delta, it can be behind or ahead, but we write it as a phase lag. Lag means it is negative. Why is it called lag? We're just thinking about the phase part, when you compare two sinusoidal functions and just looking at the phase part, a better diagram is the phasor diagram, which you learned before. So phasor diagram is just, you think of this as a vector in 2 dimensions. This is the x component of that vector. Okay, so this is the fictitious x component of with angle omega t. So theta is this omega t, right? So t equal to 0, you can draw both of these vectors, a vector for this and a vector for that, and that will tell you what the delta means. So if you draw, f looks like that, and when you draw say x, it will look like that, and that angle will be theta. I'm sorry, here delta here. And phasor is a very interesting thing, right? If you just look at this vector, omega t is changing in time linearly, right? So this arrow will be rotating at a constant velocity. This is also rotating at the same constant velocity. So although I drew it at t equal to 0 for convenience, this is the same diagram at any other time, right? You're just going to just rotate. This going to rotate this, and this going to rotate at that. This distance will be f0. This distance will be a. I hope this clears up some of the things that you may be thinking about in the phasor diagram. It's very simple. Just think of this being an x component of a fictitious 2-dimensional thing. We don't have anything 2-dimensional here. We're just thinking that way. Okay. So this thing, when you how far it lags behind, if you look at the solution tells me this delta is actually, we write tangent, it's easier to write tangent delta, and tangent of delta is gamma times omega 0 square minus omega square. Okay, let's look at some values. I want to plot. Well, you remember a plot, right? A plot starts with f0 over m omega 0 square, and it dies out like that with some omega r. I want to do the same thing with the delta. I want to see what the delta plot looks like. So when I'm at 0, omega 0 is 0, so I am over here. And when I look at the zero, I have a zero. When omega goes to infinity, both go to infinity. So you have omega go to infinity, omega large, and this becomes minus omega square, and then it becomes minus gamma over omega. So it's going to zero from negative, which means it's end up tangent delta is going to zero minus. Unlike when omega is zero, it went zero plus. So the other is going to go to pi, and so over here is going to be pi. So got 2 points, So if it's really oscillating very, if not oscillating at all, then there is no phase shift. If it's oscillating very rapidly, if omega is very, very, very rapid oscillation, then force and if the force is this direction, x is that direction. So forces they're 180 degrees apart. That's crazy, right? Force is trying to pull it this way. When it's pulling it this way, maximum, the displacement is maximum on that other side. Sound crazy? It is crazy, but you should play around with this. This is very interesting crazy. Okay. How about if I am right at the resonance of the amplitude? Well, all I have to do is just plug into this and see what value I get. Value you get is a rather interesting there also. So tangent delta for the resonance somewhere, it's going to be somewhere here, right? We have 2 endpoints, so it's going to be between 0 and pi, and it gives gamma omega r over omega naught square minus omega square. So if you remember, omega r square is omega naught square minus half gamma square. That you get by analyzing that graph. So this is a gamma omega 0 square minus half gamma square, and then this one is going to be half gamma square. So I take a gamma, cancel that out. So I have a 2 omega 0 square minus half gamma square over gamma. Kind of complicated. It's going to be somewhere here, but in a complicated way. A point when omega is omega r. Well, this complication can actually be simplified if I say I'm going to only look at systems which are seriously underdamped, meaning very good oscillators. So that kind of oscillator is called lightly damped oscillator. If I look at lightly damped, what I mean is omega naught over gamma is this is going to infinity. Okay, omega naught is way bigger than gamma. So in this case, I get 2 times omega naught square. There should be somewhere a square root missing, okay? So actually there's a square root here. Because the whole thing has to be unitless because I have a tangent of this. So that's the case. So it's almost like that over gamma. Then is 2 omega naught over gamma. So this is going to infinity. So tangent of delta A it's actually pi over 2. It's not pi over 2, it's this number, but when I get the lightly damped oscillator, then in that case it is actually pi over 2. And if you plot this out, complete this graph, it kind of starts out pretty gently here. It goes like that. And you can see in both of these cases, there is this thing, the width. And over here is also, you might say, there is a corresponding width here. And that depends on how good an oscillator you have. If you have a very good oscillator, then this width will decrease and this thing will go higher. So if I have a good oscillator, of course I'm going to start at the same place because this is independent of what kind of oscillator you got. This would be, if you can see that if omega gamma is very small compared to this, the smaller the gamma, the better the oscillator. So this will, if I make this, it's going to move a little bit, right? If I make it, if gamma is bigger, so say this was a gamma 1, some value of gamma 1, and I make it and this is omega r for gamma 2. The gamma 2 will move, this will be the peak now, and the peak will be higher, and it will be narrower. So it will be narrower. So same thing happens over here. If this is for gamma 1, so if I do gamma 2, now the width will be less. So this is for gamma 2. So gamma 2 is less than gamma 1. You might, you can think about this as in terms of how good oscillator it is. You might think in terms of a Q factor. So when you decrease gamma, means you're making damping less and less, meaning the oscillator got better and better as the Q is bigger and bigger. So you can say that as the Q goes up, this thing is getting more and more peaked, more and more peaked. Eventually it's going to be like a delta function. It's going to go to the whatever resonance it is, it go to the resonance and then it's going to jump. Where will that happen? At what point that will happen? You can see when the gamma has to be 0. That means at that point omega resonance is actual to omega 0. So somewhere there is omega 0. So when omega resonance is omega 0 value, then at that point it's going to peak like, remember Dirac delta function? It's going to be like that. It's going to be very narrowly peaked and very high peaked. So if you don't have any damping whatsoever, then the resonance will be like an impulse in the amplitude and a step function in the delta. So I'm going to stop here, and we're going to talk some other kinds of resonances later. In particular, I want to discuss the resonance of power. When the force, the driving force, is putting energy in, we want to study the rate at which the energy goes in. Of course, the rate has to be equal to the rate at which the damping part is taking the energy away, right? For the steady state, the system to be in a steady state, meaning that over a cycle, its kinetic energy and present energy are fixed. So whatever energy it takes in from the driving force, it will have to give the energy to the damping system. So I'm going to want to give a lecture on the power and the resonance of the power next. Okay, see you.